So today we're going to be talking about the Zeeman effect. The Zeeman effect is actually a really cool phenomenon that happens in physics that I had a lot of fun learning about as I prepared for this video. But in order to understand it, we're going to have to review a couple of basic concepts that we actually learned about in chemistry. So if I make a basic model of an atom, for hydrogen, for example, to start with an easy one, you have a single proton in its nucleus and a single lone electron orbiting the nucleus. And this electron exists in that first electron shell in the N1. Now, if I do a bigger or more complicated element like krypton, for example, krypton has a lot of electrons, and I won't draw the electrons, but I will draw the electron shells because in krypton there are 4 of them. 3 and 4. And so all the electrons exist in these energy levels, in these electron shells, and they're all packed in there in that quantized manner. And so what we learn in quantum physics, and I'm going to draw another hydrogen atom, but this time I'm just going to draw the proton, and you've got one energy shell and then the electron that exists here. We learn in quantum physics that if you excite an atom, that the electron doesn't stay in that base electron shell. It actually will move outward into another energy level. I'm going to draw these nice and wide so I've got space for later. And I'm going to say that we've excited this one so that it moves out to the third energy level, to the third electron shell. Now this doesn't do much until the electron decides to come back down to its base energy level. So when the electron, let's say this one goes from 3 to 1, it gives off energy. Now this energy comes off in the form of a photon. And this photon comes out at a specific amount. It's not random. It comes out at a specific wavelength, which correlates to actually a specific color. And so if you have the electron excited that moves from a different energy level, let's say this time it moves from the second shell back down to the first one, then you're actually going to get a different specific wavelength, a different specific photon that comes out, and that new specific wavelength is going to have a different color. And so I just drew red and green here. Those are arbitrary colors. I don't know exactly from what energy level to the next gives off what color, but we can do that, and we actually did that in the homework. But the idea here is that it's specific. It's not random. And so that's why it's actually called quantum physics, because it comes off quantized, not continuous. That each of these levels moving out away from the nucleus of an atom is quantized. It's the root word is quantity. I like to think of it as like a ladder. A ladder has certain rungs on it, and when you're climbing the ladder, you can't step on the ladder at a place that is in between the rungs. You can only step on the rungs. So a ladder is also, therefore, you could say quantized and not continuous. Continuous would be like a rainbow. A rainbow has no differentiation between the colors. There's no steps to it. It's not like a stair or a ladder, but this is where quantum physics come from. Now, usually when we talk about quantum physics, we talk about how photons are emitted, and we see them on a spectral line analysis. So if I have here an element that's giving off the specific spectral line, and it gives off, let's say, one red line and maybe 2 different colored orange lines, like maybe one of them's darker. Let's see if I can try to draw that with my pencil. And so every element actually has a specific set of spectral lines. So I don't know what this one is, but let's just pretend, let's say this is the specific spectral line for helium. And so this is super useful when we do neon signs, which is why neon is so popular, because the element neon in its gas form, if you put it in a glass tube, run electricity through it, or in other words, we excite the atom, then when it gives off those photons, it gives off a really nice bright color that looks really cool. And that's why we put it in the signs that say open on our small businesses and things. And every element has a specific set of spectral lines. Now, where does the Zeeman effect come into play? The Zeeman effect, if this is the atom we're still working with here, if we were to put it in the presence of a magnetic field, and I'm going to pretend this is my magnetic field generator. If we put it in the presence of a magnetic field, it messes with the emission of the photons that come out of each atom. So when before we had just one red line, now we're going to have what's called spectral line splitting, and we're going to get two or sometimes even more lines. Now, this was a strange phenomenon discovered in the early 20th century by Peter Zeeman, hence the name the Zeeman Effect. And it's a very interesting story because Peter Zeeman was influenced by his teacher, Hendrik Lorentz. So Zeeman was actually the student, and he got the name in the phenomenon, which is really neat to me because maybe if I were more dedicated or hardworking or even worked in a physics lab, I could maybe have something named after me, but I don't. But it's really neat because they actually won in 1902 the Nobel Prize in physics for discovering this effect. So what Zeeman was able to discover is not only that this occurred, that spectral lines could split in the presence of a magnetic field, but he also learned that the splitting is proportional to the strength of the magnetic field that's being applied. So if you turned up the magnetic field, you would get more splitting, and if you turned it down, you'd get less splitting. Very little is known or understood or proven about the Zeeman effect. However, Zeeman himself was able to prove that it was proportional to the strength of the magnetic field being applied. The current theories onto how this works, I'm going to draw a different model of an atom here, but it's going to be at a side angle. So if this is our proton nucleus, and this is our electron orbiting around it, and so I'm going to draw like the poles here. If it's spinning around this pole, kind of like the moon rotates around the sun, when the photon is emitted, you would think that it just goes straight off, and you would be right. But in the presence of a magnetic field, it doesn't come off straight. It comes off at these angles. And so this is the reason for the spectral line splitting. This is why we get, instead of one, we get multiple. And this was a crazy phenomenon when it was discovered, and it's still pretty crazy today. And we haven't come up with an exact formula to predict the splitting, how much splitting or how many splitting. We haven't been able to come up with like a number or an equation, like I said, to predict the splitting. We just know that it happens, and we think that it's because of this that the magnetic field affects the rotation of the spin of the photon as it comes out of the atom, according to the ongoing spin of the individual electrons from the element that you're using. And so this also is quantized because it's understood that like however much you apply the magnetic field, you get a different splitting, and you can't get a half split. You know, you can't get one line and a half a line. It's either one or two. It's, you know, integer numbers. So this Zeeman effect is also quantized and is involved in the realm of quantum physics. And so there's much more to be discovered here, but that is essentially the Zeeman effect.